Welcome to today's Vela Solaris webinar. I am pleased to welcome you all. My name is Mike Runke, and I am a consulting engineer at Vela Solaris, the Swiss company behind the leading simulation software for renewable energy systems and heat pump installations. Over the next 30 minutes, we will be discussing a topic that has recently become extremely important for planning engineers and energy consultants using waste heat from data centers. So here is a brief overview of our agenda for today. We will start with a short welcome and introduction, followed by to why the topic of waste heat in data centers is so relevant right now. After that, we will look at the regulatory requirements, particularly the energy efficiency law for data centers in Germany and Switzerland, of course. The main part will show the four most common application cases with specific hydraulic schemes, and afterwards, I'll show you how to plan and simulate these systems with the software Polysun. After the lecture, we will have about 15 minutes for your questions, and you can ask questions at any time via the chat functions, and we will answer them at the end. By the end, you will know which application cases is right for you and for your next project and how to demonstrate it with Polysun. So the development of the Polysun software traces back over 50 years. So it was 1975 when Martin Sock developed like the first foundations, the first models of what you now know as Polysun. From 1992 onwards, the models were further developed at the renowned Institute for Solar Technology, the SPF at Rapperswil, the University of Applied Sciences. In 2006, now 20 years ago, the Vela Solaris AG was established as a spin-off company of the SPF. And furthermore, we continuously calibrate Polysun alongside universities such as Kassel and Dalarna against transits and real-world measurement data. Vela Solaris we are located in Winterthur in beautiful Switzerland. Winterthur is a town or a city close to Zurich. Our software is distributed over 40 countries, and we're providing services in the field of energy system simulations. Over 1,000 engineering companies trust now Polysun for projects where mistakes can be costly. So let's start with a quote from Border Step 2024. I'll let you read it and think about that for a second. So this means almost 3/4 of data center operators do not yet know how to solve that problem. And this is your chance as a planner to simulate the proper system. Data centers are the backbone of digitalization, and yet they are among the biggest energy consumers. In Germany, data center power consumption currently stands at around 20 terawatt hours of electricity per year. That equals round about 3.7% of Germany's total electricity consumptions, and the trend is pointing straight up. According to current projections, that figure will rise to between 25 and 37 terawatt hours by 2030. So the realistic mean value is around 31 terawatt hours. The Border Step Institute, what that quote was the previous page before, even predicts that the share of data centers could increase to 6 to 7% of the total electricity consumption. So, what are the main drivers? This, I bet you all for sure know. It's the rapid expansion of artificial intelligence and, of course, cloud computing, and in general, the digital networking of our economy and society. So, new data centers are being built and they must be planned for the outset with sustainable energy concepts. And this creates enormous project opportunities for everyone involved. Okay, so let's take a look at where the electricity in data centers are actually going. The largest proportion, around 69%, goes to the IT equipment, meaning the servers themselves. 16% is used for cooling, 8% for the power supply, and the rest for ventilation and lighting. Now, for the key figure here, we have 81% of data centers' total energy consumption is generated as usable waste heat. So, when we're thinking about data centers' power consumption at scale, that is a staggering amount of energy because they run 24/7. So, the energy that is all too often released into the environment via cooling towers, for example, and that is not how we want to use that amount of energy. So this is precisely where data center heat reuse comes in, and precisely why recovering energy from servers has become a central issue in energy planning. To put that in plain terms, for example, in Frankfurt, a data center with 30 megawatt of IT capacity generates 39 megawatt of heat, enough to supply 15,000 households per year. And furthermore, the European Union intends to at least triple the capacity of its data centers by 2030. Plans include simplified licensing procedures and a strong focus on sustainability. And the new data centers will be built and they must be planned for the outset with sustainable, regulatory, compliant energy concepts. For everyone attending this webinar, the project opportunities are enormous. So, that being said, let's move on to the regulatory framework, which has seen significant changes in recent years. In Germany, the Energy Efficiency Act, the EnEfG, now legally obliges data centers to use waste heat. The most important points at a glance: from 1st of July 2026, so not within just 3 months, new data centers must use at least 10% of the waste heat. From 2027, the obligation increases to 15% waste heat utilization, and 2028, at least 20%. Subject to technical and economic feasibility, from July 2025, the obligation to implement an energy and environmental management system. It's the ISO 50001 or the EMAS. So from 2027, 100% renewable electricity for all data centers must be used. So the PUE targets, short for power usage effectiveness, being total energy consumptions of the data center divided by energy consumption of the IT equipment. So new data centers being built, a maximum allowed from 1.2, existing data centers, a maximum of 1.5 by 2027, and 1.3 by 2030. Furthermore, operators must report data on the potential for waste heat to the BAFA annually. And the waste heat must be used primarily on site or via local heat networks, rather than just simply being released in the environment and not being used. So in Switzerland, the use of waste heat in data centers is also increasingly being embedded in cantonal building regulations. So, for example, in Zurich, we have data centers with more than 2 gigawatt hours of waste heat. this waste heat must be sold to a third parties at cost price if they cannot use it themselves. In our neighbor Austria is focusing on pilot projects. Here, large buildings and clinics are already being heated with server waste heat. And the Scandinavia goes the furthest. In Finland, Sweden, Denmark, or Norway, the injection of data center waste heat into district heating networks is already common practice, with a minimum required of 1 megawatt of IT load. Now, enough of the regulations. We move now to the heart of the webinar, the most common applications for waste heat utilization in data centers. For each use case, I'll show you the hydraulic principle diagram, the typical planning issues, and the most important decision criteria. So, what do you see here? This is a standard template of our software. Everybody can access it. And we have here lines or system borders, let's say. The blue one is like the whole district, which is analyzed, and the red dotted line shall be the data center. So the data center is the core is demonstrated for the box on the right with the blue and the red arrow, and this provides like the 24/7 energy demand. So the energy here, we want to cool our servers, and the waste heat is given to the district, which is now seen with a green arrow. Respectively, if there's too much energy in the system, we have like emergency coolings regarding the red arrow. So the first and the most common application in many European cities is data center district heating. The heat from the data centers is fed into the urban or regional heat networks via large heat pumps at the temperatures of 60 to 75 degrees Celsius. So, but there's an important engineering detail here. Typically, air or water cooled servers deliver outlet temperatures of round about, let's say, 30 to 45 degrees. That's depends on the technique which the data center uses. So to supply a conventional heat network, we almost always need a heat pump or a cascade solution. And that is a core part of data centers heat recovery planning. For this application, there are three central planning questions. So question number one, is the server waste heat sufficient, or do I need a heat pump to increase the temperature level? Question number two, are the investments and operating costs economical compared to a gas boiler? And the last question, is there a network within a radius from 1 to 3 kilometers with year-round demand? Regarding the economics, the investment costs for heat pumps are 5 to 10 times higher than for a gas boiler. However, with a high COP and cheap electricity, the cost of generating heat can actually be lower than gas price. And in many countries, subsidies cover up to 40% of their investment costs. So just to give you a little demonstration of the software, we have here the system which I just showed you in the presentation, and this can be also simulated by you guys. You can go into standard and then just type in the name of the template. So we have here various um, analyzation tools. For example, the simulation analysis, which here you see we have different temperatures, flow rates throughout the system and for each component. So here there will be 1 year generated, and we see what this year is going to be like. How is my controller working? How are my heat generators working, and how much demand is taken, for example, from the district heating? There are various techniques to analyze your system. It's not just a simulation analysis, it's also the component results or the graphical evaluation. And the key component is, for example, the system comparison. This is a game changer when you're comparing different templates. Of course, they must be similar, and then you just change, for example, the storage size or maybe a bigger gas boiler or a heat pump, and then you see directly how this affects my system, and for that also my costs. Continuing, the second use case is particularly elegant and forward-looking. It's the bidirectional cold district heating network, also known here as AT3B. In this system, and this is more sophisticated take on data center district heating, the data center feeds its waste heat, which has a temperature of between 20 and 35 degrees Celsius, directly into the cold network. The connected buildings, apartments, offices, or schools, they have decentralized heat pumps, which you can see here in the screenshot. The major advantage is that due to the low network temperatures, there are hardly any network losses compared, for example, the previous one with 60 to 75%. So this follows that the heat pump works more efficiently with COP values of 3.5 or even to 6. And in summer, the system becomes bidirectional. That means excess heat from the building flows back into the network and is used for the regeneration of, here in this example, for geothermal fields or to cool the data center. This creates a genius symbiosis between data centers and the neighborhood where it's built. So our next use case is, what if there are no district heating? So like the motto would be there, if there's no district heating network in reach, the neighbor is the network. That being said, if there is no real network, the third application comes into play, and that would be like, for example, a direct supply of neighboring buildings or facilities. Typically, recipients are swimming pools and sport halls with a constant heat requirement, greenhouses and aquaculture enterprises that manage with 25 to 45 degrees, and or a campus or an office complex that increases the heat, for example, to 55 to 70 degrees Celsius. In the example from our blog, the data center feeds into like a ring net, and the indoor swimming pool, as you can see, is here the main consumer, and it covers its heat regenerations directly. Any surplus heat flows into an ice storage system, and decentralized heat pumps supply further buildings. So a key planning consideration, due to the constant waste heat stream from the data center, the ice storage system can be designed more compactly and cost efficiently. For peak load situations, short-term buffer storage or medium-term load-based operating management and seasonal large-scale cold storage are all used. As for the first one, this can also be self-analyzed. Let's say in our software, we can see here, for example, with the component results, showing each component over the year for each month, the different parameters which are being calculated over this example year. That being said, now we can, for example, see what the heat pump is doing, like respectively, how often is it going to switch on, how is the performance factor, and what are the temperatures doing. And this gives us a big advantage when comparing system, when we want to get into the detailed analysis. So also the results, if you want to export them, you can even like export them in hourly or 15-minute values, respectively. All these values which are being calculated can be checked into the graphical evaluations. Speaking, you're making the data visible. Also, the profitability calculation is a very big game changer regarding our costs and usage. Jumping back to our use cases, we have one more use case which is quite interesting and common. That would be the free cooling and heat recovery. So free cooling data centers means leveraging natural sources of cold, like outside air, rivers, lakes, or the sea. So that means we're really dependent on where we're building. To reduce cooling loads in northern Europe, this can cover a large proportion of the cooling requirement. And now in Central Europe, outer air free cooling is viable for around 1,000 to 2,000 hours per year. And that rises to, let's say, 3,000 to 4,500 hours when using a lake or seawater. Hydrothermal networks transport the cold water from the natural sources directly into the cooling circuits of data centers. The heat absorbed in that process is then increased to a usable level by heat pumps, making data centers heat recovery both the cooling solution and the energy source simultaneously. So the result, the data center is cooled and simultaneously I provide heating for the city or the location. A significant added value is created by plant simulation. Only with dynamic simulation can you determine exactly how many hours of free cooling are truly usable and how storage, heat pumps, and bypass systems can be optimally dimensioned. That we have seen in the simulation analysis, where we can check each timestamp of the year, what is going to happen with my system and does it function as I wanted to do so. So we now come to the final part, optimal planning. And this is where Polysun really comes into its own. Dynamic plant simulation enables what is otherwise impossible in the early planning phase, the exact calculation and transparent documentation of data centers' heat reuse projects. Polysun can realistically visit all four use cases that we have seen today, including heat pump, cascades, different sorts of boosters, various storage technologies, and connection to district heating, or respectively, cooling networks. So exactly what does Polysun do for waste heat utilization in data centers? As we seen in these different use cases, we have yearly trends in server loads, for example. We can check out how is the heat output and the cooling requirements in the specific simulation. We have also different system variants that can be compared directly. I showed you a brief snippet of it. Um, in the component results, for example, we can start stop cycles of the heat pumps, and we can change different sorts of controllers, let's say, to see how the start stop cycles or the overall hour the heat pump runs changes. Also, the CO2 saving potential is transparently indicated. You see that on the right side. This is when you just simulate one system, then you get a system diagram, and then this indicates your CO2 emissions, also considering on the energy mix. Meaning, if I have different, let's say, different current, different CO2 balances, then I can change that in the software so it's also in my results. And the big key fact is here also that simulation-based optimization can reduce operating costs by up to 40%. So today we saw a variety of applications: heat networks, energy networks, directly supply, and free cooling. But they all have one thing in common. They only function reliably or the, if the supply of heat and demand for heat are dynamically aligned. And this is precisely the moment when simulation stops being an option and becomes the basis for planning. It's a must do for district heating network operators. That means if you're planning or operating district heating network, data centers are an attractive source of waste heat because they deliver 8,760 hours a year, independent of weather or season. The scale of data centers heat reuse available to planners right now is genuinely unimaginable important. However, the system logics of the data center and the heat network can conflict. So the heat network requires low supply temperatures, high utilization, and cost-effective heat generation. The data center wants stable IT temperatures for the servers and as few external interventions in its cooling systems as possible. Polysun makes this conflict of interest visible and resolvable. You can simulate various handover scenarios, storage sizes, and control strategies before making a single investment decision. This creates planning security for authorities, builders, and/or investors, and it's invaluable in the early project phase. So, for the data centers operators, the conclusion is also clear. The EnEfG leaves no room for maneuver. It's being set 10% from July 2026, 15% from 2027, 20% from 2028. So these are hard facts, not recommendations. Moreover, 73%, when we go back to the quote, of operators themselves say that waste heat requirements are their biggest challenge. So transparency and quality, that would mean we have here a full documentation of the desired state, compliance, effective communications here with stakeholders based on robust data, and resilience, reliable risk minimization through simulation of extreme weather scenarios. To conclude, I would like to highlight 3 points. Firstly, this webinar recording will soon be embedded in our data center waste heat blog post at velasolaris.com/Abwärmenutzung Rechenzentren. You will also find all 4 hydraulic schematics that we presented today, as well as the regulatory details there. Secondly, you can try Polysun for free for 30 days. Simply register at velasolaris.com/en/pricing. Thirdly, if you need specific project support, such as help with design or system selections, we are happy to help. Contact us via velasolaris.com/en/contact.